Hello, my name is Tim Reid, and I'm going to be talking about prior distributions and test statistics for the Bayesian conjugate gradient method. This is work that I've done with my collaborators John Cockayne, who is at the Alan Turing Institute, Ilse Ipsen, who is my advisor at North Carolina State University, and Chris Oates, who is at Newcastle University. This work was partially funded by a National Science Foundation RTG grant. The subject of the talk is probabilistic numerical analysis. The goal of probabilistic numerical analysis is to obtain a statistical treatment of the errors from deterministic numerical methods. And the deterministic numerical methods we're going to deal with in this talk are iterative linear solvers. So suppose you're given a symmetric positive definite matrix A and a vector B, and we want to find the vector x star such that A times x star is equal to B. An iterative linear solver will produce an approximate solution xm in m iterations. We're going to use probabilistic numerics to gain insight into the error that's the difference between your approximate solution xm and your true solution x star. So now I'm going to go through a brief outline of my talk. First, I'm going to introduce the conjugate gradient and Bayesian conjugate gradient methods. Then I'm going to talk about uncertainty quantification of the error. Then I'm going to talk about choosing the prior covariance matrix. And then I'm going to go through some numerical experiments. So, the conjugate gradient method is a classical numerical method that iteratively solves a system of linear equations. It computes the approximate solution xm by starting at an initial guess and then following a set of m search directions to the approximate solution. These search directions are an A orthonormal basis for the m-dimensional Krylov space, listed in that first equation. The Krylov space is the span of the residual and succeedingly larger powers of A times the residual. What A orthonormal means is that we have a matrix V whose columns are the CG search directions, then V transpose times A times V should be equal to the identity matrix. The solution of CG satisfies this minimization property where the A norm of the error is minimized over the m-dimensional Krylov space. The A norm of the error is a weighted inner product where the weighting is the matrix A. The Bayesian conjugate gradient method is a probabilistic generalization of CG. It takes as an input a prior distribution that models the initial uncertainty on your true solution x star and returns a posterior distribution that models the remaining uncertainty after m iterations. The prior distribution is a normal distribution with mean x0 and covariance sigma 0, and the posterior distribution is a normal distribution with mean xm and covariance sigma m. The prior mean, x0, is analogous to the initial guess in CG, and the posterior mean, xm, is analogous to the solution from CG. The uncertainty in the true solution is due to our limited computational budget. So now I'm going to talk about how we actually compute the posterior distribution. You establish a random variable x that is distributed according to your prior distribution, and that random variable x models the true solution x star. We then choose m linearly independent search directions. Here they're listed as S1, S2 through Sm, and they make up the columns of the matrix uppercase Sm. We then define an information vector ym as the matrix Sm times the matrix A times the random variable x. We then compute the posterior distribution as the conditional distribution of x given ym, and that distribution is the normal distribution with mean xm, described in the first equation, and covariance sigma m described in the second equation. Both these equations require inverting the matrix Sm transpose times A times sigma 0 times A times Sm. However, to make it so that we don't need to invert that matrix, we're going to require that the search directions are A, sigma 0, A, orthonormal. And that means that the search directions will make the matrix Sm transpose times A times sigma 0 times A times Sm equal to the identity matrix. Now I'm going to talk about uncertainty quantification for the error. What we want to do is determine how well the posterior distribution models the true solution. In the paper that originally presented Bayes CG, the posterior distribution is used to relate the error to a chi-squared distribution. Our approach in this talk is to compute the distance between the posterior distribution and the true solution with the Wasserstein distance. The Wasserstein distance is a metric on a set of probability distributions. If we have two normal distributions, mu and nu, that are Gaussian distributions, then we can compute the Wasserstein distance between them using this formula that is an expression in terms of the two-norm difference between the two means and an expression involving the traces of the covariance matrices. If instead we use the A norm to compute the Wasserstein distance, the formula changes to being an expression in terms of the A norm of the difference between the two means and an expression involving the trace of A times the covariance matrices of those two distributions. If we consider the true solution of the linear system to be a point distribution at x star, then we can compute the Wasserstein distance between the Bayes CG posterior distribution and the true solution x star. The Wasserstein distance between the Bayes CG posterior and the true solution is the sum of the trace of A times the posterior covariance matrix plus the A norm of the error. The downside of this expression is that the true solution x star is required in order to compute that distance, but we can estimate the distance without needing to know the true solution x star. We're going to estimate the distance with the S statistic. So we want to estimate the Wasserstein distance, which I restate at the top of the slide. So the way we're going to do that is introduce a random variable x that is distributed according to the posterior distribution, and then we'll define the S statistic as the A norm difference between that random variable x and the true solution x star. We can compute the expected value of the S statistic, and it is the A norm of the error plus the trace of A times the posterior covariance matrix. And because of this, the expected value of the S statistic is equal to the Wasserstein distance between the posterior distribution and the true solution. The S statistic still requires knowing the true solution x star in order to compute it. What we want is a version that does not require knowing the true solution x star in order to compute it. So to do that, we're going to introduce a second random variable, x prime, that is also distributed according to the posterior distribution, and this random variable x prime is independent from the random variable x. Then we define the alternative S statistic as the A norm difference between the two random variables. The expected value of the alternative S statistic is 2 times the trace of A times the posterior covariance matrix. If the posterior distribution accurately models the true solution x star, then the alternative S statistic should approximate the original S statistic. So now I'm going to summarize the uncertainty quantification. We measure the distance between the posterior distribution and the true solution with the Wasserstein distance. We then estimate the Wasserstein distance with the S statistic, and then if the posterior distribution accurately models the true solution, then the alternative S statistic should also estimate the Wasserstein distance without requiring knowing the true solution x star. So now I'm going to talk about the choice of the prior covariance matrix. The prior covariance matrix can be any symmetric positive definite matrix. Some possible choices that we've used are setting the prior covariance to be equal to the identity matrix. That prior covariance is easy to compute, but it causes the posterior mean to converge slowly. Another choice is setting the prior covariance matrix to be equal to the matrix A inverse. This causes the posterior mean to converge at the same speed as the solution in CG. Another choice is to set the prior covariance to be the matrix A inverse squared. This causes Bayes CG to converge in one iteration. We can also define the prior covariance in terms of a preconditioner, where the matrix P is approximately the matrix A. And we can also define a prior covariance in terms of the Krylov subspaces used in CG. So some downsides of the prior covariances being the identity matrix or the matrix A inverse is that the identity matrix causes the posterior mean to converge slowly. The inverse matrix is expensive to compute, and if you have the inverse matrix, you don't really need to solve the linear system. And with both these prior covariance matrices, the posterior distributions overestimate the error. What we want from the prior covariance matrix is that the convergence of the mean to be as fast as it is in CG. We want the posterior covariance matrix to reflect the error, and we want the prior covariance matrix to be cheaper to compute than A inverse. Our solution to these problems is to introduce a new Krylov prior. This Krylov prior is going to be based on the Krylov subspace prior in the original Bayes CG paper. To make it, we choose an initial guess x0, which is going to be the same as your prior mean, and then define the initial residual as b minus a times x0. We then define a matrix V, where the columns of V are an A orthonormal basis for the Krylov space in A and R0 of maximal dimension. So this is the biggest possible Krylov space generated by the matrix A and the vector that is the initial residual. We're going to say that the dimension of this Krylov space is the uppercase Roman K. We're going to also define a diagonal matrix phi, where the diagonal entries are the columns of V transpose times the initial residual squared. And then we'll define the Krylov prior covariance matrix as gamma 0 being equal to V times phi times V transpose. So now I'm going to talk about how the Krylov prior is related to the CG search directions. The CG search directions are an A orthonormal basis to the Krylov space generated by A and the initial residual. The columns of V are an A orthonormal basis to the same Krylov space. So this means that the columns of V are equal to the CG search directions. The distance traveled along each search direction, Vi, in step I of CG is equal to Vi transpose times R0. So this means that the entries of phi are the square of the distances traveled along the CG search directions in each step of CG. Because of the A orthonormality of the columns of the matrix V, we can compute the matrix vector product of gamma 0 times A times the vector Vi, and it ends up being equal to Vi transpose R0 squared times Vi. And what this means is that the matrix gamma times A has eigenvectors Vi with the corresponding eigenvalues Vi transpose R0 squared. And what this means is that the Krylov prior is a generalized eigen decomposition, where the eigenvectors are the CG search directions and the eigenvalues are the square of the distances that you travel along those search directions in CG. There are two important consequences of the matrix gamma 0 times A having the eigenvectors being the columns of the matrix V. And the first consequence is that the posterior mean with a Krylov prior is equal to the output of CG. The second consequence is that the posterior covariance matrix gamma M is made from the same factor matrices as the prior covariance matrix gamma 0. So gamma M is made up of the last m plus 1 through k columns of V and the last m plus 1 through k rows and columns of phi, multiplied like how they are in this equation here. We can relate the classical error to the Krylov posterior covariance matrix. BCG with the Krylov prior will converge to the true solution x star in k iterations. The error is the length of all search directions that you haven't taken remaining until convergence. So what this means is that the A norm of the error for the solution, the prior mean xm, is the sum of the distance that you'll travel along the search directions from step m plus 1 through step k. By the cyclic commutivity of the trace and the A orthonormality of V, we can compute the trace of A times the posterior covariance matrix gamma M, and what we get is that it is the sum of the last m plus 1 through k entries of phi, and these are equal to the last m plus 1 through k distances that you would travel in CG. So the consequence of this is that the trace of A times the Krylov posterior covariance matrix gamma M is equal to the A norm of the error. And now we're going to relate this back to the S statistic. So we just showed that the trace of the Krylov posterior covariance matrix makes the trace of A times the matrix gamma M equal to the A norm of the error. The expected value of the S statistic is equal to the trace of A times your posterior covariance matrix plus the A norm of the error, which when we substitute in what we know the trace to be, we get that that is equal to 2 times the A norm of the error. And then for the alternative S statistic, the expected value is equal to 2 times the trace of A times your posterior covariance matrix, which in this case is 2 times the A norm of the error. So this means that the Krylov prior makes both versions of the S statistic have the same expected value. So now I'm going to talk about actually computing the Krylov posterior covariance matrix. Computing the Krylov prior covariance matrix is computationally expensive because it requires as much effort as fully solving the linear system. But computing an approximate posterior covariance matrix is more efficient. So the Krylov posterior covariance matrix is made up of the last m plus 1 through k columns of V and the last m plus 1 through k rows and columns of phi. We can create a rank L low rank approximation of this by just using columns m plus 1 through m plus L of phi and rows and columns m plus 1 through m plus L of phi. The downside of using an approximate distribution is that the true solution x star is not in the support of the approximate distribution. However, we can measure the error between the approximate and true distribution with a Wasserstein distance, and the result of that is that the difference between the true and approximate distribution is equal to the trace of the last m plus L plus 1 through k entries of the matrix phi. So this error ends up being equal to the A norm difference between your true solution x star and the vector x m plus L, where x m plus L is equal to the solution returned by m plus L iterations of CG. So to compute the low rank posterior covariance matrix, we can do it at the cost of m plus L CG iterations. The process of doing this is to run m iterations of CG to get the posterior mean xm, then run L additional iterations of CG to compute columns n plus 1 through n plus L of V, and then use those columns of V to compute the posterior covariance matrix. We can use CG to compute the posterior mean because Bayes CG with the Krylov prior and CG have the same result. So to summarize the results of a new Krylov prior, we introduced a new version of the Krylov prior, and we defined it as a generalized eigen decomposition with the CG search directions as the eigenvectors. We showed that the Krylov prior causes the posterior mean to be equal to the output of CG. We showed that it causes the S-statistic to accurately estimate the Wasserstein distance between the posterior and the true solution. And then we introduced a low-rank approximation to the Krylov posterior that can be computed with CG. Now I'm going to summarize the numerical experiments that we performed. In these numerical experiments, we're going to show that the posterior mean converges at the same speed when the inverse prior and Krylov prior are used. We're going to show that the alternative S-statistic overestimates the Wasserstein distance when the inverse prior is used, but accurately estimates the Wasserstein distance when the Krylov prior is used. We're going to also show that the approximate Krylov posterior produces similar results to the full-rank Krylov posterior. All these numerical experiments are run on the same problem. The matrix A is a 1000 by 1000 matrix with a condition number of 10,000. So here we depict the convergence of the residual in Bayes CG with the inverse prior, which is shown on the left, and the Krylov prior, which is shown on the right. The residual plotted in both these graphs is the relative residual, the norm of B minus AX, divided by the norm of A, and the norm of X. We can see that the convergence of the residual is equal when the inverse and Krylov prior is used, and this shows a verification of our result that the Krylov prior causes Bayes CG to converge at the same speed as CG. And we know this because in the original Bayes CG paper, it was shown that the inverse prior causes Bayes CG to converge at the same speed as CG. So here we show the results of the S-statistic when we use the inverse prior. For this problem, the A norm of the error is equal to 1.44 times 10 to the minus 2. The Wasserstein error and the S-statistic are both around 940, while the alternative S-statistic is around 1,880. What this shows is that the alternative S-statistic overestimates the Wasserstein distance when the inverse prior is used. Here we show the S-statistic with the Krylov prior. Here the A norm of the error is the same, 1.44 times 10 to the minus 2 power. The Wasserstein error, the S-statistic, and the alternative S-statistic are all around the same value at 2.8 times 10 to the minus 2 power. So what this means is that the alternative S-statistic correctly estimates the Wasserstein distance. And you can see this in the plots, where the plot on the left is the S-statistic and the plot on the right is the alternative S-statistic, and both of them have around the same distribution. Since the mean of the S-statistics is around 2 times what the A norm of the error is, we can use the S-statistic to estimate the A norm of the error as well. And here we have the S-statistic with a rank 5 approximation to the Krylov posterior. The A norm again is 1.44 times 10 to the minus 2, but in this case, the alternative S-statistic, which is around 2.6 times 10 to the minus 2 power, slightly underestimate the S-statistic and Wasserstein error, which are around 2.8 times 10 to the minus 2 power. So this means that when we use an approximate Krylov posterior covariance matrix, the S-statistic slightly underestimates the Wasserstein distance. However, in the plots, we can see that the S-statistic on the left and the alternative S statistic on the right both behave similarly to when we used the full-rank Krylov posterior covariance matrix. So now I'm going to summarize the results that we presented in this talk. We measured the distance between the posterior distribution and the true solution with the Wasserstein distance. We then estimated the Wasserstein distance with the S statistic. We introduced a new Krylov prior and showed that it causes Bayes CG to converge at the same speed as CG, and we showed that the S statistic accurately estimates the Wasserstein distance when the Krylov prior is used. We also introduced an efficient method to compute an approximate Krylov posterior covariance matrix and showed that it behaved similarly to the full Krylov posterior covariance matrix. These are the sources that I cited throughout my talk. Thank you for listening.